the lecture. We'll get started in just a minute. We are currently finishing up talking about nomenclature, chapter 3, a continuation from what we talked about last week, I guess it would be. And we'll continue on in just a second. Again, a reminder that if you keep all your cameras off, which you are doing right now, so I appreciate it, so we don't get so many boxes. And again, this is still being recorded and should be uploaded shortly when we're all done in the next day or so. Again, you can find the recordings up on our Canvas site in the little section that says recorded past lectures. And if you do have a question, again, you could ask it in the chat area. That's usually the best way to do it. I will get to your question for sure. Even if I'm talking, I'll come back to your question. All right, so we're going to continue on talking about nomenclature. So last time we talked about nomenclature, we talked about type 1 compounds. And again, a type 1 compound is a metal and non-metal. And always when you have a metal and a non-metal, the important one is the metal. And type 1, that's group 1, 2, 3. It is zinc, cadmium, or silver. And what all those have in common is they have fixed charges. So because they have fixed charges, essentially what that means is we don't have to worry about anything in terms of indicating the charge. We just use the whole name of the metal. And our non-metal there gets the IDE at the end of it. And that would be something like CaCl2. CaCl2, calcium is group number 2, has a fixed charge of +2. So this would be calcium chloride. And we also talked about type 2 compounds. Type 2 compounds are also ionic, and they're also a metal and a non-metal. Also here, it is the metal that's important. It is a transition metal. Are just to the right on the periodic table. And those guys can have a variable type charge. So the important thing when we go to name these guys is we still do pretty much the exact same thing. We're going to use the whole name of the metal. We're going to do our non-metal. Drop the last part there and replace it with the IDE. But these are the guys that do need a Roman numeral. So we use our Roman numeral. And a reminder that the Roman numeral is the positive charge on the metal. So if we took one of the metals out by itself, what the positive charge would be, that's what the Roman numeral indicates. So if we had something like FeCl2, iron is a transition metal, so we would have to figure out what the charge is on it. But we do know Cl is group 7, so it has a -1 charge. And again, there's 2 of them, gives you a -2 overall. And that gets us to +2. So we would name this as iron Roman numeral 2. And again, the 2 for the charge on the metal. And even though we have 2 chlorines there, or chlorides, it is still just called chloride. No prefix or anything like that, just iron 2 chloride. Again, the 2 indicating not how many metals you have, which is a very common mistake people make. It is indicating the actual positive charge that we have up there on our metal. Then we finished up talking about polyatomic ions there in lab. And polyatomic ions are basically groups of nonmetals together that have ions, that have charges associated with them. So something like NO3 minus, again, that 1 nitrogen, 3 oxygens are all together. It's covalently bonded together through sharing of electrons. And it all has a -1 charge, and this is what is known as nitrate. While if you had something like NO2 minus, that 1 nitrogen and the 2 oxygens there also stay together as 1 unit, as it is bound together through sharing of electrons, and that is what is known as nitrite. And the general way that most of these polyatomic ions are related to each other is they're essentially related to each other by a different number of oxygens. So the one with the least number of oxygens typically will end in ITE. The one with the most number of oxygens will end in ATE. There's also a group of 4 sort of polyatomic ions that are related. And they also work the same way, except that the one with the most starts with per and ends with 8. And then you have 8. And those are the 2 that would have the most oxygens. And then the least oxygens would end in ite. And in a group of 4, the guy with the least number of oxygens in a group of 4 would start with hypo and end with ite. So for example, ClO4 minus and ClO minus. These are all related to each other with ClO3 minus and ClO2 minus. So this guy with the most oxygen starts with per, and it becomes chlorate. This guy with the least number of oxygen starts with hypo and becomes chlorite, with chlorite here and chlorate here with the 3 as the other names that you would give these guys, and this group of 4 that are related to each other. Again, you could swap out the Cl for something like Br, and it would be bromate, bromite. It would be named pretty much the same way. Now, for the most part, all these polyatomic ions are essentially negative, except for perhaps NH4+, that is the ammonium ion. And the ammonium ion is probably one of the only positive sort of guys that you'll come across, which means typically our polyatomic ions are going to be hooked up with a metal. And basically what that means is if it's type 1, you don't need a Roman numeral. If it's type 2, you do need a Roman numeral, just like normal. And again, the other thing that we talked about, there are some polyatomic ions that actually end in IDE. So things like OH minus is hydroxide, CN minus is cyanide. So they can end in IDE, but a vast majority of them do end in either ite or ate. And that's really a good way to sort of remember it. Sometimes people will remember like all the eights and know that the ites are just 1 oxygen less, charge is the same, or vice versa. Sometimes people will remember all the ites and know that the eights are essentially 1 oxygen more, same charge. So those are a couple ways sometimes people will do that. Also a reminder that if you did have something like this, where you do have more than 1 polyatomic ion, you do have to put that polyatomic ion in parentheses to indicate that you do have more than 1 of them. And we would name this just like normal. This is calcium, no Roman numeral needed because calcium is group 2. And even though there's 2 of the nitrates, it is still called nitrate. Any questions on any part of that nomenclature stuff that we sort of talked about last time into lab? We talked about it as well. Any questions? And again, in the notes, and then also I think in your book and maybe online as well, there's a polyatomic ion table. You are responsible to know those. Again, they will not be provided for you. Any questions on any of that? Okay, so before I scribbled on the screen, the next thing that we're going to talk about is acids and basically how to name acids. And acids, as it says on there, if you could kind of see between all the writing that I did, an acid is basically something that is able to produce an H plus ion in solution. There's an empty screen, perfect. And that's your basic definition pretty much of an acid, is that ability to produce H plus ions in solution. When we talk about H plus ions, H plus ions are sometimes called a proton when we talk about acid and bases, and that's because a hydrogen has one proton and one electron and no neutrons. So in order for it to become positively charged, it had to lose an electron, which obviously would leave it just a proton. And that's really what makes something an acid, is that ability to produce not H plus combined to anything, but really produce free H plus floating around in a solution. And certain things can produce H plus, a lot of it really quickly, and those are strong acids. And some can produce maybe just a little bit of H plus in solution, and they're considered more weak acids. So when we talk about naming acids, it is really all about our good friend oxygen and whether or not the acid has oxygen in it. So first off, if we go this way, and the answer is no, we do not have any oxygen. What that means is if you have an acid that does not have oxygen, it will start with hydro. So it's going to start with hydro, and it's going to be hydro something ic acid. So hydro something ic acid. So for example, if I take HCl and this has no oxygen in it and it's hydro, the missing part is the negative guy. So that is hydrochloric acid. Now you will see this symbol here, which is the aqueous symbol. And the aqueous symbol implies it's a solution. And that is basically what an acid is. It has to be basically a solution or a water environment. And you typically do put the little aqueous symbol next to the formula for an acid, and that's how we get hydrochloric acid. Again, that is the distinction between, say, something like HCl that has a G next to it. HCl with a G next to it is not hydrochloric acid. It would actually just be named hydrogen chloride. So that's sort of the two words there. But hydrogen chloride, again, two words. And again, that's sort of the difference there. When you take something like hydrogen chloride gas and you kind of bubble it through water, that's essentially where you get your hydrochloric acid in that case. So typically, to know it's an acid, or when you write formulas of acids, typically you should put that little aqueous symbol next to it to indicate that. So if you had something like HBr, also when we look at it, no oxygen involved. So this would become hydrobromic acid. If we had H, I, thinking about what letter I want to use there, sorry. HI is hydro, I'm just bringing a delay on the computer. Hydroiodic acid, and so forth. So Sometimes when people want to name acids, they want to use that like hydro with every acid name that they do. But hydro is specifically only used in a situation where we do not have oxygen involved. Any questions on that? And clearly, if you're given a name that has hydro in it, it should automatically tell you you do not have oxygen involved. So, for example, if you had hydrofluoric acid, as soon as you see that hydro part, you know it has no oxygen. Fluoric is fluorine. Remember that the cation for all acids is H plus. So the positive guy for all acids is going to be H plus, and that means that the fluoride here would be our negative guy, and we would know that this should be HF. Again, you would put the aqueous symbol there to indicate that it is an acid. So that's an important part as well. If you have to write the formula, this is always your cation when you're dealing with acids, your positive ion. Any questions on that? Again, if you do have questions, feel free to ask, and I'll definitely get to them. All right, then let's talk about what happens if we do have oxygen involved. So if we do have oxygen involved, it's a little bit more sort of complicated in terms of how you go about naming these guys. So if we do have oxygen involved, so the answer is yes to oxygen. What that means is you will have probably one of those polyatomic ions. And if you have one of those polyatomic ions, as we just talked about, they typically will end in one of two ways. They will end in ate, or they will end in ite. And depending on which way the polyatomic ion ends as to how you will name it, so we'll go this way. If the polyatomic ion ends in ate, your acid name will be something ic acid. So if we take HNO3, again, when we look at it, we do see oxygen, and NO3 is nitrate. So this becomes nitric acid. We take something like H2SO4. It does have oxygen. SO4 is sulfate, so this becomes sulfuric acid. Yeah. The reason we have two H's here, again, the cation for an acid is H plus. The sulfate is -2, so it really is an ionic compound here. So we do need two of those H pluses to basically balance out the charge here. It gets us +2, along with our -2 gives us 0. So again, if you put the formula together, you want to make sure you get to 0, and the positive guy always going to be our H plus. Now, if we do have oxygen and our polyatomic ion ends in ite, the way we name the acid is something OUS acid, if I don't run out of room there. And that means that if the polyatomic ion in the acid has that ITE, that's how we would want to name it. So if we take something like HNO2, again, it has oxygen here. NO2 is not nitrate, but it's nitrite. So this becomes nitrous acid. If I had something like H2SO3, SO3 is SO3 2 minus, that's sulfite. That becomes sulfurous acid. So really, uh, naming acids all involves oxygen and whether or not oxygen is there. So again, if there is no oxygen, then that is the only place, as you can see hopefully on the screen here, that is the only place where you should use hydro. So you use hydro something acid. And if it does have oxygen, again, it's going to be one of those polyatomic ions. So you would want to either use something ic acid if the polyatomic ion ends in 8. A good way to remember that is you ate too much, you feel icky. And if the polyatomic ion ends in ITE, the acid should end in OUS. Again, as you can see, if the acid has oxygen in it, there should be no hydro anywhere. So again, people always want to kind of just use hydro on every acid name, but again, only with no oxygen. Any questions on how to name acids? And also, if you do have an acid, say something like HClO4, again, you would take the same approach. So the same approach here is I see oxygen. The ClO4 is perchlorate, which means it ends in ATE, which means I should take this root. And we still keep the per in front of that, so this becomes perchloric, again with the IC acid. So again, if the polyatomic ion has one of those sort of prefixes like per or hypo, you would still keep it as you go to name the acid. Any questions on that? Okay. All right, then that is naming. Yes, good. We're down to one last type of things to name, and these are type 3 compounds. So type 3 compounds are different than type 1 and type 2. As it says up there, type 3 compounds are covalent molecules. So type 3 compounds basically are when two nonmetals come together. This is the type of bonding that we talked about where you have sharing of electrons happening. And really, these are the easiest to name, but they really are the ones that people screw up the most because they want to do all kinds of stupid things. I'll say it, stupid things, yes. So you shouldn't do those things. This is actually the place where everybody maybe doesn't want to use it, but this is actually the correct place to use prefixes when you name things. So with type 2 compounds, this is actually the correct way or correct place to use it. Again, you shouldn't use prefixes on anything in type 1 or type 2. You really shouldn't use prefixes with your polyatomic ions unless the polyatomic ion has a prefix in the name. But this is actually where you use it. So we use those prefixes like mono means 1, di means 2, tri means 3, tetra means 4, penta means 5, hexa means 6, hepta means 7, we'll go with octa means 8, nona perhaps means 9, could be making this up, let's see, deca means 10. So these are the prefixes that we typically use, and there are a couple sort of rules that we do with this. The first one is we do not use mono on the first name, but you can use it on the second. And the other thing that usually will occur as we use these prefixes are with the prefix and the first letter of the element, we will sometimes get a couple of vowels that will sort of back up to each other. So perhaps we get two O's, we get an A and an O. So it's typical to get rid of the A in the prefix or the O in the prefix. And basically how we name these are we use the whole name of the first element and then the appropriate prefix if needed. And then we use the prefix for our second element. And the second element ends like normal, kind of the non-metal with the IDE. So prefix and that first whole name and prefix, and just like we've been doing on everything else, that second guy gets the IDE. So for example, if we look at something like CO, again here, carbon is a nonmetal, oxygen is a nonmetal. So that means we should use prefixes. There's only one carbon, so the prefix is mono. There's only one oxygen, so the prefix here would be mono. So if we go to name this, as we talked about, we do not use mono on the first name. So we would just use the whole element's name, which is carbon. And then we could use that prefix on the second one. And then the second guy is named the exact same way with the IDE. Now you can see this, if we left the O, would be called carbon monoxide. And it's not really called that. It is called carbon monoxide. Yeah, so we would drop that extra O off of the prefix because, again, we get the two O's to back up to each other. The most common ones that you really should kind of avoid, an A and an O, like I said, two O's to back up to each other. You get a couple of I's, most people think it's okay, so most people will leave the two I's. Seems to be okay, but these are the two really main ones that, you know, if you come across, you want to watch out. Any questions on that? Right. So let's take a look here, maybe. Oops, wrong way. Try that again. So as I mentioned, the rules for naming these guys, again, we want to always go in terms of the formula. The first element comes first. So again, however it's written in the formula, we want to go first element first. Again, we're going to use the whole name of that guy, and we are going to use a prefix, just going to not use mono on the first one. The second one is named like everything else there that we've kind of seen. We're going to put the IDE at the end of it. It also will get a prefix. And again, it is okay, like we did in the previous example there, it is okay to use the mono on that second name. Let's see here. And here's a table of those prefixes. I think I did pretty good there. So we got di, tri, tetra for 4, penta for 5, hexa for 6, 7 is hepta, and octa is 8. Again, here, these are really the easiest because there's no charges. You don't have to worry about balancing anything. It is just simply looking up the formula. If you have the formula and go, oh, there's 2 of those and 3 of those, and picking the correct prefixes, and again, just adjusting the IDE on that second element's name. So there's no Roman numerals on this guy either. So again, only prefixes here. Don't be mixing things, otherwise it will be wrong. Yeah. Okay, let's take a lookie. So here's just those couple of things that we talked about. And on the bottom, there are a couple of important things as well. There are certain things that do have common names and should go by as common names. And obviously the big one down here, yes, H2O is water. It is not a trick question when you see that. Yeah, just write water and move on with your life. Yes, it is not dihydrogen monoxide, even though technically it is, but nobody wants a refreshing glass of dihydrogen monoxide, right? People would rather have water. So if you do see H2O, again, that's obviously what you should use. NH3 over here is ammonia, also should be called ammonia. We don't typically call it nitrogen trihydrate or anything like that. Again, ammonia is the correct name for that. That should also not be confused with NH4 plus that we saw in the polyatomic ion. These two guys are different, yes. So that is the ammonium ion. It is an ion, it has a charge. This, no charge, not an ion, basically a nitrogen and 3 hydrogens bound to it. So that's two things that get very commonly, let's put an X to it, very commonly sort of confused with each other. So again, make sure that you know that that is ammonia. Another very common one that you come across a lot is CH4. CH4 is what is known as methane. It is the simplest organic molecule you could have, basically one carbon bound to 4 hydrogens. So methane, again, is usually also just referred to by its common name. So those three for us, you should definitely know the common names. Again, methane, ammonia, and water. Any questions on that? All right. So why don't you take a second and name these three, and then we'll talk about it. And I'll give you actually a couple of names, and you can write the formulas for them as well. We'll see how everybody did. So in addition to what you got on the screen, write the formula for dinitrogen pentoxide, carbon tetrachloride, and all right. So names for the guys on the left, formulas for the ones on the right. So take a moment or two, and then we'll talk about it. Okay, so let's take a look here and see how we're doing. Again, these should really be the quickest ones for you to do. Again, because there's no balancing, you don't have to worry about charges. You essentially just need to write what the formula tells you. So if we look at the first one here, we see that we have I, which is a nonmetal. We have O, which is a nonmetal. So automatically we know we don't have to worry about balancing anything. So we see two of the I, so that's going to be di, and then we're going to use the whole name, iodine, for the first one. The second one, the prefix for 7 is hepta, and then the oxygen becomes oxide. Here we will drop that A off of that. Hept oxide. Again, as I mentioned earlier, the two I's still okay. So diiodine, heptoxide. Any questions on that one? Again, coming down here, we have carbon, which is a nonmetal. We have oxygen, which is a nonmetal. We have one carbon, so the prefix is mono. We have two oxygens, prefix is di. As we talked about before, we don't use the mono on the first name, so we're just going to use the whole name here, which is carbon. And then we will use the di on the second, and then the oxygen becomes oxide at the end. So that is carbon dioxide. And last one down here, we have phosphorus. Again, we have only one of them, which is mono. We have 3 chlorines, which is tri. Again, because mono we don't use on the first one, we're just going to use the whole name there. So that's phosphorus and trichloride. Any questions on any of those 3 names, where they came from, or any of that stuff? Okay, and then what I think is probably the easiest ones out of all of them is when you're actually given the name for these type. So if you can recognize them as type 3, it is super quick to write the formulas. So the way we can recognize them, obviously, if we're given the name and we see those prefixes, that automatically tells you it's type 3. You don't have to worry about charges. You essentially write what's there. So dinitrogen, di means 2, nitrogen is N. So we have N2. Penta is 5, and that's oxygen. So O5 in this case. And again, the nice thing is you don't have to worry about any type of balancing charges. Here we don't see a prefix, but we do see a prefix here as tetra. So tetra means 4. And because this guy's got a prefix, that must mean that this guy is 1, right? For mono that we don't use. So we would write C, and then tetra is 4, and chloride Cl4. So carbon tetrachloride in that case. Any questions on those 2? Same thing down here. We're going to see the prefixes. So we're good in that case. So oxygen is O, di is 2, penta is 5, and bromide would be Br5 in my made up thing here, O2, Br5. Any questions on how to name type 3 compounds, either the formula, write the formula, or give the name for it? Any questions on any of that? And also any questions on any of the naming? Obviously, you do need to be able to do both ways, if you will. You need to, if you are given the chemical formula, you need to be able to properly name it correctly. And before somebody asks, yes, spelling should count in this case. Yes, you should try to spell it correctly. It's kind of the whole point. And if you are given the name, you need to correctly be able to write the correct chemical formula for it. So you need to be able to do that for all the ones that we talked about. So I think at this point we should be done with naming in terms of that. Mostly we have type 1, that is metal, non-metal, no Roman numeral. Type 2, metal, non-metal with Roman numeral. Polyatomic ion is typically type 1 and type 2, so either needs a Roman numeral or not, depending on the metal. Type 3, which is our covalent compounds, will need prefixes. And nowhere along the way, again, do we see anywhere where it mixed over that you were doing prefixes with Roman numerals. Again, if you find yourself doing that, you probably should mark the X yourself, because again, it is going to be wrong. And again, the last thing that we sort of talked about there, which was acids. And acids, if it does not have oxygen, will have hydro and end in ic. If it does have oxygen, then it will either end in something ic acid or something OUS acid. And again, acids depend on oxygen. One last thing, since we're talking about naming and some of the stuff I think we talked about a little bit beforehand as well, but since it is sort of naming, remember hydrates, like that experiment we did. Hydrates are basically a salt, and it has that weird formula with the dot that has a certain number of waters attached to it in this crystal structure. So again, if we had CaSO4 dot 5H2O, we would name this just like type 1 or type 2. So this would be, type 1. So that is calcium. We don't need a Roman numeral. Sulfate. And the way that we name the water when it's a hydrate is we do say hydrate instead of water. And we would use the same type of prefixes here. So that would be pentahydrate. So that is the way we name those hydrates. And if you had something that did need a Roman numeral, this would be copper with a +2 charge, and that's because the sulfate has a -2 charge, which means if we go to name this, we'd do it like type 2, copper, Roman numeral 2, sulfate. And again, here it would be pentahydrate. So obviously we would use a similar type of prefixes when we name hydrates. Any questions on that? That should be all the naming you ever want to do until, of course, you take the next class and there's a whole bunch of weird names that you also do. But for us, that should be everything that you has to name and write the formula for. Any questions on any of it? This also will complete the final part, or the last bit that is on the next exam, and we'll talk about when that exam will be and everything at the end of the lecture. But this is the last part for, I guess that would be exam 2, I think. Yeah, so this is the last part of information for exam 2. Yeah. Okay, any questions on that? All right, we're going to continue on. Again, the lecture notes that we're going to continue on with will be for the exam 3, and they are up on Canvas. So I'm going to stop sharing for just a second, go find that one. So we can continue on. Gotta go. the right one or not. All right, give me 1 second here. Apparently didn't like the thing it clicked, so let's give that another try here. Go with that one. Just short interlude here. Let's see. All right, let's give it third time, maybe the charm. Let's see. Yeah. All right. All right, so we're going to pick up, and again, this is going to be the next chapter, and our next couple of chapters. So this is a little bit from chapter 5, which will not be on exam 2, and the rest of it is from chapter 6, basically. So it comes from these two couple of chapters. So really in these chapters here, we're going to first talk about chemical equations, how to balance chemical equations, and then we'll talk about how to identify reactions as a certain type, as either a way to classify reactions when we look at it. So the first thing we're going to talk about then is a chemical reaction and a chemical equation. So when we have a chemical reaction, it is usually a result of a chemical change that occurs. And in a chemical reaction, a reminder that we don't lose anything along the way. We basically just rearrange everything. So all the elements on one side basically rearrange to the other side and make new compounds on the product side. So when we look at a chemical reaction, the first couple of things on the left-hand side are our reactants, which are our starting material. On the right-hand side of the arrow, those are our products, and those are the guys that are made. These are things that are formed as a result of the chemical reaction. So left-hand side reactants, right-hand side products. And other things that we typically will see sometimes above the arrow, we'll sometimes see a little triangle that's used, and that usually means heat. You may see water written above the arrow, which usually means that you dissolve something in water. You may actually see something like platinum or some type of metal, or something like H+, which means an acid, and these are sometimes what are known as catalysts. And sometimes on top of that arrow, catalysts are written. And what catalysts are, they are not a reactant. They're not a product. And they actually do not get used up. They are simply there to make the reaction occur faster. Yeah? So usually a catalyst is added to speed up a chemical reaction. There's actually catalysts that slow down chemical reactions, but most of the time when people look at it or sort of consider a catalyst, they usually are talking about in the sense of speeding up a chemical reaction. So if we look over here down here at our equation, 2H2 plus O2 makes 2H2O. This is what is referred to as a balanced equation. And when we have a balanced equation, we always want to make sure that essentially what that means is we have the same number of elements on each side of the arrow. So essentially what that means is because there's conservation of mass, conservation of the elements, we again do not lose anything as we go from left to right in a chemical reaction. Again, everybody just breaks apart and they come back together. Other things that we typically will see also in formulas, we'll see S, we'll see L, we'll see G, we'll see AQ. And again, these are typically written next to a formula and they indicate the state that that guy is in. So obviously S is solid, L is liquid, G is gas, and AQ we talked about with the acids basically means a water environment that you make a solution. A reminder that the difference between L, which is a liquid, and AQ, which is basically a solution, is if you have something that's an L, that essentially means that you have one thing by itself. Like if you just had water by itself, nothing else with it, it would be considered a liquid. While if you had aqueous, it really means a solution. So if you took something like sodium chloride and you dissolved it in water, that would give you an aqueous solution of sodium chloride. So that's sort of the main difference there between these things. Any questions on that as I try to get this thing to click the right one here? Let's do it. All right. Any questions on that? Okay. So there's a couple different ways that we could actually read a chemical equation. And this is actually going to be something that's going to be very important when we get to the next sort of lecture or chapter after this one, and when we talk about stoichiometry. So we can look at those coefficients in the balanced equation and essentially say, for example, that there are two atoms of magnesium react with one molecule of O2, gives us two formula units of magnesium oxide. So formula units is something that is used really for ionic compounds. So you'll see people use formula units, and that's sort of a specific type of word that's used for an ionic compound. So instead of saying a molecule of O2 or a molecule of magnesium oxide, people don't use molecule magnesium oxide because it's ionic. So it's not sharing electrons like a molecule would be. It's more of an ionic compound, and sometimes people use this formula unit instead. But really the relationship that we'll use the most is the mole to mole relationship that you may be familiar with when we start talking about stoichiometry. And that also comes from the coefficients. We could say that there are 2 moles of magnesium react with 1 mole of O2, gives us 2 moles of magnesium oxide. The last sort of relationship here is the conservation of mass. So since we have basically the same number of magnesiums on each side and the same number of oxygens on each side, since they both have the same molar mass, the magnesium on the left and the right, we should start with about 80.6 grams of reactants, and we should end up with 80.6 grams of product, again, because we have not lost any element along the way. Again, it's not a gram to gram sort of relationship. Any questions on that there? So let us talk about then balancing equations. So we're going to talk about sort of the steps to balance chemical equations. And when it's all said and done, a couple important things. When we do balance equations, the only thing that we should ever change is the coefficients that come in front. So we should only change the numbers that come in front. Again, for example, if you have something like water, you would never want to change that number there because then it would no longer be water. You also don't want to do anything weird that sometimes people do, like I'm just going to throw a big number in between and hope for the best. So don't do any of those things. Again, the only thing that you should change is the coefficients. And once you get it correctly balanced, there is a couple of rules. All the coefficients need to be whole numbers. And they need to be the simplest set of whole numbers. So what that means is, let's just say, for example, you have that equation, you balance it with 2a plus 4b, and that gives us, we'll go with 6ab. We'll suspend belief there and believe it's balanced. So if we ended up having this equation here that's balanced, we could see that we could reduce down all these numbers by a factor of 2. And if that is the case, you should do that. And the correctly balanced equation, again, will suspend belief and believe it's balanced, would be something that looks like this. And that sometimes can happen because people sometimes can see sort of the larger numbers, if you will, to balance them. And you could use a bunch of larger numbers and it will all be balanced. And again, sometimes people won't see those numbers. So if you could reduce down all the coefficients by a common number, you should do that. If you can't, then obviously that would be the balance equation. So those are the two really main things. All the coefficients has to be whole numbers, and it has to be the simplest set of whole numbers when you go to balance it. So if you are given something in words, for example, and you need to balance the equation, the very first thing that you should do is always just write the correct formulas. So sometimes people get in a lot of trouble when they try to do this, when they try to both write the formula and balance the equation. They try to do that all together at the exact same time. And what they end up doing is usually writing the wrong formulas, and they'll never get anything to balance or anything like that, and you'll be there all day. So the order in which you want to do this is first write the equation, the correct formulas, and then balance the equation. So if we look at this, if we put down the correct formulas here, ethane is C2H6 plus oxygen, which is O2, gives me CO2 and water, which is carbon dioxide and water. So sometimes people, when they first go to balance it, will sometimes make a table, and that could be helpful sometimes. You could have on your reactant side and your product side and kind of list everything. You got carbons, you got hydrogens, and you got oxygens. And you can see on the left-hand side, you have 2 carbons. On the right-hand side, you have 1. Left-hand side, you have 6 hydrogens. Right-hand side, you have 2. Left-hand side, you have 2 oxygens. And right-hand side, you have 3 oxygens. And again, this gives you sometimes a good starting place to balance. So perhaps you might want to start with the carbon. Looks pretty easy to balance. You could put a 2 there. That obviously would change what you got going on the right-hand side. You would have 2 carbons, still the 2 hydrogens, and 2 times 2 is 4 oxygens here, plus 1 more over here would give you 5 oxygens. Any questions on that there? So again, as I talked about before, you don't want to ever change any of the little numbers. You should only change the top number there. Hang on 1 second here. All right. Sorry about this. Just give me 1 second here. All right, let's try this here. Okay, do that. Okay, so again, always the coefficient. So if we do that, we would put our 2, just like we did there. And again, what we could then go with after that point is we could go with the hydrogen next, which would be the easiest. After we made our table, we could see that we have 6 hydrogens on the left-hand side, and on the right-hand side, we have only 2 hydrogens. So to fix that, we can simply put a 3 on the right-hand side there to fix it. And when we do that, we will then balance out our hydrogen. And if we do our little table, we can see carbon, hydrogen, oxygen at this point on the reactant side and product side. The reactant side, we have 2 carbons. Sorry about that. And 2 carbons on the product side. Hydrogens is 6 over there and 6 over there, and 2 oxygens. And oxygens on the right-hand side, we have 4 there, plus 3 more, give us 5. So at this point, we were able to balance carbons. We're able to balance the hydrogens. We now have that little issue here in terms of the oxygen. And to sort of help us with that, there is a way that we could do that. So the way that we can do that is we need to use a fraction. So you can use a fraction, something like 7 over 2. And what that would give you if you sort of added everything up in terms of carbon, hydrogen, and oxygen, you would have 2 carbons on the left. You would also have 2 on the right. Hydrogens, you would have 6 on the left, 6 on the right. Oxygens, 7 over 2 times 2 would give you 7. And we would still have our 7 on the right, which means that technically speaking, this is a balanced equation, right? Now, the one thing that we did talk about was when you are done, all these coefficients has to be whole numbers. So this demonstrates that you can use a fraction to balance, but you actually do need to clear it when it's all said and done. So in this case, we need to multiply not just a fraction by 2, we need to multiply everybody by 2 to clear the fraction. And if we do that, we will end up with the correctly balanced equation by multiplying that 2 across. And again, we can see here that everything would be balanced on both sides in that particular case. Now, when we do use a fraction, it very commonly happens when you have the element by itself on one side and you got the element on a couple guys on the other side. You sometimes have to use that fraction. So the very simple rule for the fraction, so for example, if you remember in this case, we use 7 over 2. The top number is the number you need. The bottom number should match this number that's there. So that's a very easy way to pick the right fraction. Top number is always the number you need. Bottom number should match there, and you will get that. So sometimes you do have to use a fraction to balance it, which is perfectly fine. But the important part is you do have to make sure that you clear the fraction when it's all said and done. Any questions on how to do that? I apologize for some of the technical difficulties here today. All right. Why don't you? I think you got one coming up, if I'm not mistaken. So why don't you take a second here while I try to work on a little bit of these technical difficulties and try to balance this one, maybe the next one that's on your notes as well, and then we'll talk about it in just a second. Okay, so I think I got that all worked out. Sorry about that. Thing kept dropping off my screen. So again, like I said, sometimes we go to balance. It's very helpful to make a table, kind of leads you maybe in the right direction. So if we look on the left-hand side, we have one nitrogen. On the right-hand side, we have two. Left-hand side, we have one oxygen. Right-hand side, we do have one. Left-hand side, we have two. And right-hand side, we have two. So right off the bat, we can see everything's balanced except for the nitrogen. So that would be a great place to start. Again, we're only going to put coefficients. So the 2 is going to go in front. That will then give us two nitrogens. Our oxygens will also go up to 2 as we multiply the 2 across. And our hydrogens will remain at 2. So as you may be familiar with, you will sometimes fix one thing and then kind of screw up the rest. So the next probably easiest thing to balance at this point will be our oxygen, as we are missing it. So on the right hand side, we can also put a 2 in front of where the oxygen is. That's going to give us two nitrogens. Oxygens will now become 2, and then hydrogens now become 4. And that's okay, because now we could come back over here and put a 2 there, and that will give us two nitrogens, two oxygens, and our 4 hydrogens. Again, this would be a balanced equation. Any questions on that one there? Okay, so let's take a look at another one here. So why don't you give this one a go, and then we'll talk about it in a sec. All right, so let's take a look at this one here. We got on the left-hand side there 3 carbons, looks like, and on the right-hand side 1 carbon. Left-hand side we have 8 hydrogens and 2 on the right, 2 oxygens on the left, and here we have 2 oxygens plus 1 more here, gives us 3 oxygens. So again, you should hopefully see that perhaps carbon is the easiest to start with. We're going to put a 3 there. That will give us 3 carbons, it will give us still our 2 hydrogens. Oxygens, we're now up to 6 there, plus 1 more makes 7. So again, we fixed the carbons, kind of messed up everything else, and the next easiest thing to fix should be our hydrogen. So we'll put the 4 there. Still going to have 3 carbons. Hydrogen is going to be 8. And our oxygens are now up to 6 and 4. That's a lot there. I'm going to go with 10 in that case. And looks like now to finish that off, we will come to the left-hand side, and we just need to put a 5 there. And it looks like that is correct what you got going there. And we'll end up with 3, 8, and 10. Any questions on that one? And again, that's typically what you want to do, kind of back and forth until everything sort of falls into place, and it usually should. If you find yourself really struggling to balance, and you might want to check to make sure you have the right formulas, because that is oftentimes when people truly sort of struggle and sit there all day trying to balance something that might not. Any questions on that one? All right. So looking at this one here, again, if we had it in words, we want to translate it into correct formulas. So in this case, if we have our reactants and we have our products, we have boron, oxygen, and hydrogen. On the left-hand side, we have 2. Right-hand side, we have 1 boron. Left-hand side, again, we have 3 oxygens there, plus 1 more, gives us 4. And on this side, we do need to distribute this number into both of them. So the oxygen would be 3. Hydrogen on the left is 2. Same deal. We're going to distribute that number in. Gets us 3. In this particular case, not much to work with. So to fix the boron, we could put the 2 there. That gives us 2 boron. We also need to distribute the 3 to the oxygen and that 2 as well. So 3 times 2 is 6. And same thing for our hydrogen, 3, and then times the 2 on the outside gets us 6. That means to fix the hydrogen, we can put a 3 on the left-hand side. That will give us 2. That will give us now 3 oxygens there and 3 more there. Gives us 6, which actually fixes the oxygen. And 3 times 2 is 6 in this case. So in a case like this, obviously on the right-hand side there, you need to distribute the coefficient through. And you also obviously need to distribute the subscript in there as well in the parentheses. Any questions on that one? All right, so I think we got one more. Why don't you give this one a go? And we'll talk about it in a minute or so. Okay, so let's take a look and see how we're doing. All right, so on the left-hand side, we have 1 nitrogen. On the right-hand side, we have 1. Left-hand side, we have 3 hydrogens, and right-hand side, we have 2. Left-hand side, 2 oxygens, and right-hand side, we have 2. So it looks like everything's balanced except for the hydrogen. So that's where we would probably want to start. Common number between 3 and 2 is 6. So get our hydrogens over here on the left-hand side to 6. We would need a 2 to get our hydrogens over here on the right-hand side to 6. We would need a 3. So since we put numbers on both sides, let's see what that does. That's 2 nitrogens. We'll see how badly you messed up, maybe. And 6 hydrogens. And we have 2 oxygens on the left. And on the right-hand side, we have 1 nitrogen. It happens. We're all human, right? So it is 6 hydrogens. And also our oxygens, we have 1 there, and 3 more is 4. So we screwed up everything else, but fix the hydrogen. So the next easiest thing there is to fix the nitrogen. And to fix the nitrogen, we could probably just put a 2 in front of the nitrogen on the right. That's going to give us 2 nitrogens. That will still give us 6 hydrogens. We are now at a lot of oxygens there. We got 2 in the first guy, and we have 3 in the second. So that's going to be 5. So at this point, we balanced the nitrogen, we balanced the hydrogen, and we just have the oxygen go. Clearly, at this point, we don't want to mess with any of these numbers. Otherwise, we're starting again. So basically, the goal here is to turn our 2 into a 5. So this, again, would be a very good place to use a fraction, yeah? So again, the number on top is the number you need. So in this case, we need 5, right, on that side. And again, the number on the bottom should match the subscript, which it does here. It is a 2. So we would want to use something like 5/2. Again, that would give you 2 nitrogens, also would give you 6 hydrogens, and would give you 5 in terms of the oxygen. This technically is balanced, but bad, right? Because we still have a fraction. So we do need to make sure that we get rid of the fraction. So we're going to multiply, again, not just the fraction, but the entire thing by, I think they call that the denominator still, even with new math. And we're going to end up with 4NH3. We're going to end up with 5O2. We're going to end up with 4NO. And then we should end up with 6H2O. And if we didn't screw up anything, it should still be balanced. So we have 4 nitrogens on the left. We have 4 on the right. We have 4 times 3 is 12 hydrogens on the left. 12 hydrogens on the right, 6 times 2. 5 times 2 is 10 oxygens, and 4 oxygens here, and 6 here, which would be 10. So this would be your correctly balanced. Any questions on that? So again, a lot of times you do have to sometimes use a fraction. It's kind of the best way to balance it. And much like the previous example here, a lot of times when you have sort of the element, especially those diatomic molecules by themselves, you oftentimes have to use a fraction. Any questions on balancing equations there? Let me just see if I have perhaps a spot I do. Any questions on any of that? Okay, so one last thing here, and I think we'll wrap it after this here for lecture, and then we'll talk about the exam and everything that's coming up in just a second. But sometimes, let me just try to do it off the top of my head here. Okay, so since you look at an equation like this and you notice a lot of our good friends there, these polyatomic ions in it, and if you see polyatomic ions in it, and they look the same on both sides, sometimes it's a lot easier if you sort of take the approach to perhaps keep them together and balance them as kind of units rather than going element by element. So, for example, if we look at this, we see on the left hand side we have one sulfate. On the right hand side here we have three. So we could put a 3 in front of there to balance the sulfate. When we do that, though, it also changes the calcium to 3. So that would be a good place to go next and put the 3 in front of our calcium. And that gives us 3 calciums, but again, also gives us 6 now of these nitrates, which means we could come back over here and put a 2, gives us 6 nitrates, also gives us 2 of the Fs, which works out very nicely for this as well. So when you have equations that contain polyatomic ions in them, sometimes it's a lot easier, as you can see what I just did there on the board. It could go a lot quicker to sort of keep those polyatomic ions together and balance them as sort of whole units rather than going sort of element by element. You can go element by element. You just have a lot more, obviously, with polyatomic ions of multiplying in, keeping track of all those sort of elements. So sometimes it's a lot easier to balance equations that way. Any questions on balancing equations? Okay, so we will stop there today in terms of lecture. Let's talk about a couple of things. First off, exam number 2, which is, I believe, chapter 3, chapter 4, and chapter 5, not including, obviously, chapter 5 from this lecture here, but that should be, I think, grams, moles, Avogadro's number. That also should be, I think, empirical formula, molecular formula, I think, out of that chapter. These guys were the Lewis structures, right? Geometry, right? Polarity, hybridization, right? That was all those chapters. And also nomenclature, right? So exam 2, I think, is currently scheduled. I think next week is spring break, right? And I think it's currently scheduled for the Tuesday we come back, technically. So we're going to move it to the Thursday we come back, I guess. That's good, I guess, yes. So we'll put a happy face there, right? That would be a date that's in April. And it starts with a 4, I'm assuming, right? And probably ends with a 20. And is that like the 16th, perhaps? Yeah. I think that's 4/16, I think, if I'm not mistaken on that. Double check. There will be an announcement on Canvas on this, but it should be 4/16. It will occur on Canvas. And again, you'll get more instructions as we get closer to it. Just to give you a heads up, as we sort of talked about the exam, you will answer everything through Canvas online. There will be problems where you will have to show your work, which means kind of like your labs and everything like that. You'll need to be able to, after the exam, be able to, again, kind of scan your work into a PDF file, for example, maybe using Adobe Scan or something like that, and upload it as part of the exam. So in terms of the exam, my goal is I'm going to try to write the exam as best as I could do online to look like the exam that we would take in person. So it will be formatted the same way as kind of how we do it in person. So there will be a multiple choice section, which you obviously will not have to show the work for. And there will be like a written part or section of the exam, just like in person, like we did on exam one, where there may be some questions there where you will have to show the work. You will not have to be on cam during the exam. So we're going to do the whole honesty policy and all that good stuff, yes. So how the exam will work, and again, you'll get some more information, but you will have to sign an honesty agreement. The exam will be available only for a short window of time for you to take it. Once you do start the exam online, it is not going to stop the timer. So you'll have a specific amount of time to finish the exam. Once it starts, you cannot stop the timer, even if you click away or anything like that, it will continue to go. So as we'll talk about, obviously, before we take the exam, you want to make sure that you are completely ready to take the exam. And you have a calculator, you'll have some paper to show your work on those problems. The reason you're going to need to show your work is because if you type in the wrong answer, at least I could look at your work and give you some partial credit if it's possible. So yeah, so everybody probably got a little notification about exam one makeup. So just to clarify, unfortunately, there's no way to not give everybody that notification of that module being up. Just so everybody's clear, exam one makeup is only for a specific number of people that for a verified reason has already contacted me that was not able to take the exam, which we took right before we pretty much were not allowed back on campus. So exam one makeup is just for those people who already know who they are the only people that should even worry about that at this point. As we get closer to exam two, there will be another one up there for exam two that you could look at. So um, yeah, if you want to read the online, you can read the little thing that did pop up today, which is basically just kind of the instructions for online exam taking. They will be very the same. Yeah, they are the same sort of rules and instructions in terms of what's up there. So if you want to read them, you can. There will be a specific one for exam two that I will put up there, but it'll be very similar to what's up there. But you may see something over the next couple of days about exam one makeup. Again, just so we're clear, it's not like you get a chance to take exam one again. This is just unfortunately because of everything that happened. There were some verifiable sort of reasons somebody might need to make up an exam, so obviously I had to do that one online as well since we weren't allowed back on campus. So exam one makeup, again, only for those people that know about it. But if you want to read the little thing which I think popped up today was the online exam taking sort of instructions, you can. It will be a very similar sort of format as to what it says in there as well. The exam is one attempt only, so you don't keep going until you get it right. It's like a regular exam. The way I'm going to set it up, like I said, is I'm going to try to write it so it looks just like a regular exam that we take in class, which means that you will be able to see every single question all at once. And that just like a regular exam, you can kind of scan through and answer what you want to answer first, go back to whatever you want to answer later. Um, with that being said, as we'll talk about, there will be pretty much one button at the very bottom that says submit. And obviously you would not want to submit the exam until you've completed the entire exam. And again, we'll talk more about that as we get closer, but since you have available to you all the questions, you should only hit the submit button once. If you hit the submit button early before you finish the exam, you will submit an incomplete exam and it will not be reopened for you. So do not hit the submit button until you have completed the entire exam. So you will have to sign sort of a academic honesty agreement that outlines things. This is still considered an exam, just like you would take in person. It's closed book, it's closed notes. And by the way, there's still going to be different versions. So you should not do anything dumb when you take the exam. And you should still not have the right answers on the wrong version or anything like that. So the answers that you answer online do need to match the work that you're going to upload. So they do need to match. Again, if they do not match, like you had second thoughts after you submitted the exam, I will not look at your work. So they do have to show the exact same work as the answer you submitted online. To answer your question, you will be given, like normal, a conversion sheet of any type of conversions that you need. You'll also be given a periodic table. Again, you will not be given any formulas like normal. So those, again, you do need to know, but you will be given all the same information. And like I said, I'm going to try to format it as close to like the exam we take in class. So it's not so strange to you. It will be strange taking it online, but it won't be so strange. Any other questions on that? We will get talk more about it, obviously, probably on Tuesday before it, but those are sort of the highlights. The other highlight is, again, the exam will be open for a specific period of time for you to take it. You will be given a certain amount of time to actually take the exam. You do want to make sure that you start the exam with enough time left in the availability window to give you your full time period. So for example, let's just say that the availability of the exam, it is over at 4:00 p.m., which it probably wouldn't be, but let's just say 4:00 p.m. And you decide to log in at 3:50 p.m. The computer will only give you 10 minutes to take the exam. You will not get your full time. So you want to make sure you look at the availability of it, and I'll tell you how long it will be available for, but you want to make sure that you start the exam with enough time to get the full amount of time. Again, if you wait too long to start the exam, you will have whatever time is left. Kind of like in person. Like if you walk in with 20 minutes to go, you get like 20 minutes left. So it's kind of worked the same way, okay? So you want to make sure you start the exam, obviously, in enough time to finish it. Any questions on that? And again, there will definitely be a lot more sort of information coming your way. You may even see some things up online about exam one makeup. Again, that is only for certain people, and you should not have to worry about any of that if you took exam one already. You don't have to worry about it. Any questions on that? To be truthfully honest with you, from what I'm understanding, I don't think we're, I won't say ever, but for this semester, we're not going to probably meet in person again. So the entire class has moved completely 100% online. There will be no more in person for sure for this semester. And my hunch is probably for summer school either. It will be probably very similar to this, 100% online as well. So I wouldn't anticipate any in person anymore for this semester. At least that's my understanding at this point. Again, things could change, but from what I'm seeing, it doesn't seem like we will. So in terms of the exam, like I said, there'll be a lot of stuff that you'll have to kind of do as you go through it, and I'll give you more information on that. In terms of labs, scheduled for today was an actual lab. Since we're just getting into reactions, what you should still have out there is study assignment C, which I think is nomenclature, and study assignment D, which I think is kind of grams and moles and all that kind of stuff. These, again, study assignments can be found in the back of the lab manual, and that's where you'll do them. So these two here will be due on, I think, since technically spring break next week, we shouldn't meet or have anything due. So probably the 14th, the Tuesday after that technically, is when those will be due. So for lab today, I am going to open a lab session. And again, I'll be there to answer questions. If you have questions on study assignment C or study assignment D or anything we've been talking about, I'll be happy to answer that for a little bit. I'll be there. And again, you'll see on Canvas a spot to submit those, and I'll make them available pretty soon if I haven't already. So if you knock it out in the next week and you just want to be done with it, you could upload it and be done. But they'll officially be due on the 14th, those two. When we come back technically on that week, we'll continue talking about types of reactions, and we'll pick up that double displacement reaction. And I think on the schedule, there's some more study assignments as well. So we'll pick up all that kind of stuff. Experiment 7, thank you. I was just going to mention that should be due whatever day I put up there. I don't recall off the top of my head, but it should be due, I would think, either today or tomorrow. I forget which day I put. But make sure that you do submit experiment 7, which again should be only part 1. That was the only part that was in the video. And make sure that you look at the due date, and it gets submitted by the due date. It should be a formal lab report that's typed and needs to be uploaded. Again, typed lab report, carbon pages, pre and post lab questions. I think I saw some people already uploaded it already, so that's good. Make sure that you don't forget about that. Homework will also be due on the day of the exam, so you'll have to upload your homework, and there will be, again, an assignment spot for you to do that as well in the module section. Any questions on anything before we sort of finish lecturing? Everything will be sort of graded like normal, and I do take into consideration, taking it online and everything like that. So I try to give you enough time to kind of take that into account, doing everything online. In terms of grading it, everything will still be graded kind of like normal. Now, I would recommend that if you get any emails from the president of the college or the college itself, admissions records, or any of that type of stuff, I know because of the situation, perhaps the colleges are allowing certain options that maybe are not normally available to students because of this. Things like maybe an excused withdrawal or something like that. So I wouldn't, if you get emails from sort of the college and stuff like that, sometimes we want to ignore them. You might want to make sure that you look at them because they might have some important information about maybe certain things that they may be doing that are normally not allowed, but may be allowed in this semester and stuff like that. So you may want to just make sure you read those things. But in terms of this class and how everything will be graded, it'll be graded like normal. You're still expected, obviously, to do everything and submit everything. Any other questions or anything like that? Okay, so like I said, I'm going to take a break, stand and stretch it a little bit. In maybe about 15 minutes or so, maybe about 7:30, I will open up the separate lab session. And again, I'll be hanging out there for a while. If you feel like you need some help on any of those study assignments or anything else, again, you're more than welcome to pop in and ask questions. And other than that, have a good weekend. If I don't see you in lab for this particular point, have a good spring break. Since it is technically spring break next week, we won't have any live lectures next week. So we'll pick up after spring break like normal. And other than that, if everybody's good here, I will see you. I will see you when I see you, I guess, online. All right. Have a good night. And again, we'll start the lab in about 15 minutes at 7:30.